So today we will review things that we learned last year about logs, just our basic definitions and how they work. So first off, we want to remember that logarithm means exponent. We can write things in either logarithmic form or exponential form. And log means exponent, so this first equation, log equals L, so the log is L, so L is the exponent when you talk about the other form, the exponential form. It is important to remember that they both have the same base, which is b. For a log, it is written as a subscript. For the exponential form, it is the one that is on the main line, not the one that's up high as the exponent. We talked when we were doing graphs of exponentials about how the base had to be positive. We talked about we weren't going to do exponentials where we were taking negative to a power because we wanted that to be defined for all real numbers. And if we took negative 4 to the 1/2, we're not going to get a real number for the answer on that. We also talked about we didn't want to do 0 to a power, that was too boring. And so we talked about, and so that's part of why the base has to be positive. We're going to refer to this number n as the argument of the logarithm. Your book will also refer to it as anti-log, but that's a topic that we've chosen not to really work on here, so we have replaced a lot of the anti-log problems in the problem sets with things that are more meaningful for you guys to work on. But the anti-log would be this argument of the log, or it would be the answer when it's in exponential form. And it must also always be something positive. So I'd like for you to get these two equivalent formulas into your formula list just so it's easy to find when you are looking back for that. And then we will zip through a whole bunch of examples of going back and forth between these and solving some very basic logarithmic equations. They will go very, very fast because they are just very basic ones. But last year, this was something new to you, and then you've had all summer to forget about it. So we need to make sure we remember how these things work. For me, when I'm doing them, I always remember that they have the same base, and then the other parts kind of flip. What was with the base for the log is now by itself. What was by itself in logarithmic form is now the one that's by the base in exponential form. Or to remember that when it says on here on the left, the log equals a, the log is a, the log is the exponent, so a is the exponent when I come over to the other side. So it looks like you guys have that down. Let's run through these real fast. So for the first one, here it is in exponential form. To put it in logarithmic form, I need to keep the same base. The base was 3 on the left, so the base is still 3. The log is going to be the exponent, or I'm going to switch sides. The 3 was with the 2, so now the 2's by itself. The 9 was by itself, now it's with the 3. Over here on the right it says the log is 2. The log is the exponent. 2 is indeed the exponent in the original question on the left. Is that making sense to everybody? Okay, Chloe, take this next one. How do I write this one in exponential form? Or I'm sorry, in log form. Log base 1/2 of 1/8 is, so the log is 3. 3 is the exponent. We kept the same base. Does that work for everybody? Okay, Avery, how about the next one for me? Log base 4 of the log needs to be the, so of 72 is, so the log is x. X is the exponent in the original question. Jack, do the next one.
Log xy of 35 is.
Is that much making sense to everybody? Okay, let's do 4 where we go back the other way. Let's see, Abby H. How would I put this one in exponential form? And that happens to be true, doesn't it? So that means that the log equation that they gave us was also true. Okay, next one. Kian, would you convert this one for me, please? And that has two variables in it, so it's not something that we can solve, but that would be the equivalent form. How about this one? Kensley, help me out with this one. So the log is 8. 8 is the exponent. Again, two variables, so not something that we can solve at this point in time. Ryan, take this one. So the log is -4. -4 is the exponent. That one only has one variable. So we could solve this one. And the easiest thing when you've got a fraction to a negative power, the negative sign turns the fraction upside down. So 5/2 to the 4th is equal to c. If you have trouble with that, yes, you could do 2 to the -4 over 5 to the -4. That means the 2 to the 4th could go in the denominator with a positive exponent. The 5 to the -4th could go in the numerator. But faster to just upside down, and then everything's to the 4th power. So help me out here. 5 times 5 times 5 times 5. What's 25 times 25? 625, I think I'm hearing. What about 2 to the 4th? 16. So we actually just solved what that one was equal to. So far, so good? Okay, then let's solve some more. And I'll show you a couple of different kinds of tricks that you'll come across in these things. So first I need to convert this one to exponential form. That is always one of the tricks that we can choose to use as we are working through trying to solve some of these things. So let's see. Who should I pick on here that I haven't lately? Gina, convert this one for me. So b cubed equals 64. So I know that means I need to take the cubed root of both sides. And what is the cubed root of 64? What? It's 4. Do I need to worry about plus or minus for the cubed root? No, so we're in good shape there. Okay, let's try this one. Billy, would you convert this one for me? So the log is -1/3. -1/3 is the exponent. Okay, this one's a little bit harder than that first one, because the first one I clearly knew I needed to take a cubed root to undo things and get b by itself. But this is a little fuzzier. However, I modeled on example 9 what the trick is going to be. We know we want to have b to the first, right? That's our objective whenever we're solving. B all by itself equals. So what I did here when I wrote the cubed root as 1/3, I wrote the fraction that when I multiply those powers, I'd get 1. So for this one, what I need to do is to take both sides to the -3, because when I multiply these powers, -1/3 times -3, I get 1. So that means I need to take this to the -3 as well. Everybody with me to there? Got a question, Grace? A little bit louder, please. 1/3 can't be a square root. I could have put that 1 over b to the 1/3, so 1 over the cubed root of b, but then that's still going to be hard. This is the fastest way I know of to take the power on both sides that'll make the exponent just be 1. So then that means I am looking at 1 over 4 cubed, or from what you told me on example 9, 1 over 64. Questions? Let's do 2 more. So this time we have log base 2 of 1/16 equals x. These are no calculator problems when you see this kind of stuff, so don't try to just start punching it in your calculators. We need to convert this. So Kyle, would you set this one up for us, please? Okay, not quite as obvious as some of the others, but I've got 2 to a power in this thing. Be nice if I could have everything as 2 to powers, right? Do I know 16 as a power of 2, Ariel? 2 to what equals 16? So I know that 2 to the 4th is 16, so I know I've got 2 to the x is 2 to the minus 4. When I have the same base, the exponents have to be equal, so then I can simply say x has to be -4. And our last one for today. So Avery, would you set this one up, please? Okay, so we just need to evaluate that. And from what I just talked about a minute ago, with the minus sign, let's flip the fraction upside down and make that be 5 to the positive 3 is m. So m is how much, everybody? 125. So are we good with this new material? Any question?